How you doing? I'm Mr. Rose, and we're going to continue to work through a few more examples of Gauss's law. I'm going to continue to separate them, maybe problem by problem or every two problems. Um, but again, we're doing this a little bit differently. I'm going to work through the problems as I go, but I recommend, as always, you pause, try and work through, and then see if we get the same answers. What is really weird for this for me is they always, don't look at the camera. Do I look past the camera? Where do I look? I'm not really sure. So hopefully this is working out for you. All right, so for this example, I've taken the liberty of drawing an electric field. It's a uniform electric field going from left to right. And I want to know, well, what maybe the flux is, say, for some arbitrary shape, like a cylinder. So I'm going to draw a cylinder straight in here. My cylinders are not the best drawings. Now I drew that kind of distinctly for us to see that the cylinder is made up of three pieces. I'm going to say piece A, piece B, and piece C. So what we're going to show here is that there is no enclosed charge. What we should remember is Gauss's law is talking about, we can write it again, an enclosed integral of E dot dA is equal to Q enclosed over epsilon naught. So here I had this uniform field, and I should know that, well, there is no enclosed charge. And remember, we are measuring the flux. Charges in, charges out. So if I had a charge density out of the same number of lines, obviously I only have one here drawn, I'd have the same number of lines going in, going out, which would show by inspection that there is no enclosed charge. So we're going to show that a few other ways. Mainly, I want to say maybe I could find the net flux. Well, again, the flux is that airflow. That's, again, the electric field going through this. We might remember that Gauss's law has equal to something. So I'm going to say that that flux, which we denote as that capital phi, is equal to my enclosed integral, or my surface integral, of E dot dA. So now I can show the net flux. Well, I'm proving that my net flux is zero. The way we're going to do it, like I said, is applying our Gauss's law, and I distinctly made three surfaces. I'm going to choose three surfaces to be surface A, surface B, and surface C. So what do we have here? We should notice that we have a kind of a rectangle, kind of a circle, kind of a circle. That makes up my cylinder. So I have three surfaces, and I'm going to apply Gauss's law across every surface. So I'm going to say that's the enclosed integral, or my surface integral, of surface A for E dot dA. Plus, I know we're obeying the law of superposition. Surface B of E dot dA, and label these A, B, label this C, plus my enclosed integral of E dot dA for surface C. All right, well, we know that I can label that R. I can label my vector dA in that direction using my right-hand rule. And I can do the same thing here, radius R, vector dA. And I actually have no incoming or outgoing charge here. I have nothing that I could do. So I know that that is zero. That's the easy part. Well, E dot dA here is going to be E cosine theta plus 0 plus E, I guess, C cosine theta. I guess I can have my denote my E through A, my E through C. Well, theta here is 180 degrees because my dA is in the opposite direction of my electric field, which means theta here is going to be 0 degrees because my dA, my vector that represents my area, is in the same direction as my electric field. Well, that's super easy, even though I don't know any of these numbers. I know that when I have a cosine of 180, that is my minimum, or I should say a maximum in the negative direction, times cosine of 180 degrees, plus EC times the cosine of 0 degrees. Well, I know EA is really just E. E times A, and that's in the negative direction, plus 0, plus E times A, the area of that, times times cosine of 0, which is positive, negative EA, plus 0 plus positive EA, will come out to a net flux proof of 0. This we could have done by inspection, and I could have said that. I could have said by inspection, I can see that the net flux is 0 because I have a negative flux here and a positive flux there. Or I can do it mathematically to show no enclosed charge. So this example was relatively easy. We could do it mathematically, and the math wasn't very hard. We had no numbers for that, but again, we could just do that. We could just do that by simply applying an application of Gauss's law and once again, utilizing symmetry. It's our symmetry arguments that make this so powerful. That's all I have for this quick example. Tune in next time or just go on to see the next example. The next example is going to be some three-dimensional cube with flux coming through different surfaces. Thank you. That's all I have. Please feel free to like, click, or subscribe, and you'll see me next time.